Welcome to this fifth and last lecture. Just like Walter before me, I would like to thank Ali for organizing this great conference and inviting me. I really had a great time here. And also thank you to all the people at the Math Village. You really made us have a great stay, so I'm grateful for that. And so I promise that during this last lecture I will tell you a bit more about what I do in my own research regarding weighted words that I presented yesterday. So I will do that in a minute. I just want to add some information that I haven't told yesterday about why it's interesting to have non-dilated versions of theorems. Because we saw yesterday that when you have a refinement, it's nice because it gives you more combinatorial information, because instead of having two big sets of combinatorial objects that are equinumerous, you can split these sets into smaller sets, and that gives you an idea of how to find the bijection. So that's the interest of a refinement. But why is it interesting to have a non-dilated refinement, right? Because so far we could say, okay, it's more or less the same. But actually, not exactly, because here I copied the non-dilated version of Schur's theorem that we saw yesterday. So if you want to find Schur's theorem, you can do some dilations that I told you yesterday, which correspond on those variables to doing, so replacing Q by Q3, A by A, actually if you want to find Schur, you just replace A by Q minus 2. Or if you want to keep the refined version of Schur, you can also keep the variable A as you wish. And B, you replace by BQ minus 1, or without the B if you don't refine as you wish. And yeah, so then the matrix translates to the difference conditions of Schur, and this becomes just distinct parts congruent to 1 or 2 modulo 3. So that's just, okay, that's how you get Schur. But actually, you can get infinitely many other partition identities, because once you are here, you can actually do any other dilation that you want. So any other dilation. I don't know if you want if you want something crazy. I don't know, like you can take you can send Q to the 149 or whatever. I hope it's not a multiple of 3, otherwise. No, that's good. And A to whatever, like Q to the minus. I'm just picking random numbers in my mind. And I don't know, something like that. And then you will get a new partition identity. So here you would get like distinct bars congruent to minus 7 or minus 34 modulo 149. Well, it's probably not that interesting, this particular example, but actually you can really do whatever you want. So you get infinitely many new identities. Okay. So actually, you could also do some dilation of Q in Schur's original theorem, but because it's already modulo Q3, then you could only get moduli that are multiples of 3, whereas in the non-dilated version, you can really get anything. But okay, it's infinitely many identities, but they are still related with each other in the sense that if you try to compute their non-dilated version, you will always find this one. So it's still in some restricted family, but still, you can do much more like that. And also, especially in the work of Aladi and Gordon, they also like to play with the order, and if they change the order of the numbers here, they also get some other identities. But I didn't want to insist on that too much, because of course I cannot talk about everything. So yeah, you have more possibilities. Okay, so actually, now I will talk to you about my research as promised, or a subset of it, which is concerned with weighted words and partition identities that come from Lie algebras. So, okay, let's say weighted words. That will be the title of my video. And partition identities from the algebra representations. Okay. So, until now I have tried to be quite thorough and really prove almost everything that I told you. But today it will be a bit different. It will be more of an overview of some results that I got. But don't expect any proof today. Okay, so who knows what a Lie algebra is in the audience? Okay, so not so many. So I just recall the definition, but even if you don't know, it's okay. I will just try to give you the idea of what is happening, but maybe just the definition of Lie algebra is still useful so that you have some idea of what we are talking about. So a Lie algebra, the definition is actually not too hard. It's a vector space, and we'll call it like a big cursive G that is always hard to draw, together with a bilinear map. Which we write as a bracket, and which is called the Lie bracket, so it makes sense. Such that, so you have two conditions. The first one is that for all x in our Lie algebra G, we have the Lie bracket of x with itself, which is 0. And there is another condition, which is called the Jacobi identity. I can put that a bit higher, because so far there is nothing on the other blackboard. And this identity tells you that for all x, y, z in G, you have bracket of x, bracket of yz, sorry, plus bracket of z and bracket of xy, and bracket of y and zx equal to 0. So that's just a definition. If you want actually a simple example, I can give you one. But maybe I leave it as an exercise to you to check that those two properties are true, but like a very classical example, you have some Lie algebra which is called an-1, and it's called the special linear Lie algebra. Oops, Lie algebra. And it's simply the algebra of matrices. So it's the n by n matrices with trace 0. And the bracket is quite simple here. You just take, if you have two matrices like that, you take xy minus yx. Okay. And I'll give you two last definitions. So we said that we were studying Lie algebra representations, and so far we only know what a Lie algebra is, so I think we should also know what a representation is. And maybe the rest, it will be okay. I will just give you ideas. So, okay, so a representation of G, that's often also called the module of G. It's, yeah, we use either word indifferently. So that's also a vector space. So we like vector spaces here. So a vector space V together with a linear map this time. Linear map, what do I call it? Rho. So from G to no, that I shouldn't do, some crazy G to GL of V, such that rho of the bracket of xy is equal to rho of x, rho of y, minus rho of y, rho of x. Okay, so actually, if we take our example here, we could do something very trivial. We could take the identity actually for rho, and we could take an for v. That's not a super interesting representation, but like that would hold, right? Because of the definition of the Lie bracket we just gave. But usually, we study Lie algebras that are a bit complicated, and in general, we like to find representations that are a bit more simple algebraically than the Lie algebra we study. Otherwise, there is no point really if it's just to consider the identity. But yeah, so that's the idea behind representation theory, is to represent complicated algebraic structure by more simple ones. So, okay, so that's what a representation is. And, okay, so last thing that will be useful to make the connection with partition identity is something called character. So, to define a character, I will need some particular representations or modules, but I won't really define them if you don't mind, because yeah, if I give all the definitions, that would take like, I don't know, a whole semester, so let's just be, I hope you don't mind, because then I promise you would have the idea of what I'm talking about, so I try to keep the definitions to a minimum. So, trust me, there are some particular modules. Yeah, so I don't know. Usually I use module more than representation, but that's just my... It's because in the articles I read first, they were always saying modules, so I took that habit. So there are particular modules that can be decomposed in some sense as a direct sum of other modules. And this sum is indexed by some mu. You don't need to know what that is. It's a weight, but, well, I'm not saying what a weight is, so either you know and it's good, or you don't know and it's also good because you won't need it later. Okay, so there are some particular modules that can be decomposed in that way. So you believe me, and for those modules, you can define the character of the module. So the character of V, and which we write CH of V. That's simply some kind of generating function for the dimensions of those subspaces V mu. So you sum over the same mu. It's okay if you still don't know what it is. You just have to notice it's the same of the dimension of V sub mu times exponential mu. You don't know what, well, you still don't know what mu is, so you don't know what exponential mu is either, but that's okay. You can just think of it as a formal exponential, so like if you multiply exponential mu and exponential mu prime, you will get exponential mu plus mu prime, whatever that means. Okay, so the representation theorists, they like to study the character because like knowing all those dimensions, that gives them a lot of information on their modules V. So it's a bit like when in combinatorics we study a generating function to study a combinatorial object. More or less. I don't know if they would fully agree with me, but at least that's how I see it personally. And yeah, so those and the characters are objects with whom the connection with partition identities has been done. So that was done by Lepofsky and Wilson, but unfortunately I haven't written the date exactly, but that's in the 80s. Yeah, I hope you won't mind if I just write 80s. So Lepofsky and Wilson, yeah, in the 1980s. They said that if you take the Rogers-Ramanujan identities, so you remember, or maybe I rewrite the Rogers-Ramanujan identities, why not? That never hurts, right? So we have qn squared divided by qq sub n, which is equal to 1 over q, q4, q5, infinity. You remember that, huh? Right? And actually what they connected with the character is not exactly the Rogers-Ramanujan identities, but the Rogers-Ramanujan identities times some factor, which they call the fudge factor, and I'm not sure exactly why this denomination, but anyway, that's how it's called. And they showed that this equals the character of some module V of some Lie algebra. So maybe for those who know, and for those who don't, it's okay. So V is, where am I? Yeah, so V is called the standard. I'm not going to say what standard means, only if you know you recognize. Standard level 3 module of A11. So we just saw A and minus 1 here, so that's something. And actually, so A1 would just be this thing when you put n equal to 2, and A11 with the 1 on top. That means that you take the infinite dimensional Lie algebra that corresponds to this one. So again, it's okay if you don't know the details, but just think it's a bit related to this example. Okay, so that's, this is a sentence more for those who already know, because I know there are a few in the room, so I'm trying for my lecture to be like several different levels of difficulty at the same time for the various levels of expertise. So actually, so what did they do to do that? So actually, for the right-hand side here, and I'm going to pick my red chalk that I like. So the right-hand side here. So actually, that was more Lipovsky and Milne than Lipovsky and Williamson. So that's also in the 80s, but a bit earlier. So that they showed that it is the principal specialization. I will explain what it is. Of the so-called Wildcats character formula. So that I will not tell you what it is exactly, but I can tell you that it's a formula for the character. That makes sense. And it's quite complicated to begin with, but actually when you do some substitutions in the variables that appear in this formula, then you get infinite products. So here that's exactly what they do. So actually it's the principal specialization. I promised that I would tell you what it is. So the Lie algebras, they have some particular objects called simple roots, and for those who know. And let's say those simple roots are called alpha 0 up to alpha n. The idea of the principal specialization is to transform all the exponential minus alpha 0, etc., just up to exponential to the alpha n by q, very simply, where alpha 0, etc., alpha n are the simple roots. And if you don't know what the roots are, it's okay. You just think, I don't know, we have some formula with a lot of variables, and we transform everything into q's to get our q series that we like. Okay, so that's one side. And actually, that wasn't easy, but it's the easier side. This side was really complicated to interpret in terms of Lie algebra. And actually, what they did for this side, maybe I'll do some, oops, I go here. To do that, they constructed, so this time it was Lipovsky and Wilson. They constructed bases of the representation. Yeah, so like they construct bases, and then therefore they can find the dimensions, and yeah, more or less that's the idea. And to construct those bases, they use they use the theory of they use some relations that exist in Lie algebras, and actually they were able to construct some monomials that corresponded to the difference 2 conditions of Rogers-Ramanujan. So that's more or less the idea of the connection. I'm not fully claiming that everything was well defined, but I hope you at least have a grasp of what the ideas are. And so that was the start of a very, very fruitful interaction between the two fields of partition identities on one side and representation theory of Lie algebras on the other side. Because after Lipovsky and Wilson worked on that representation, many other mathematicians have worked on other Lie algebras with similar methods, or the same Lie algebra at some other level. You don't need to know what the level is, but it's some parameters that you can fix for your representation. So actually there are so many possibilities, because you can change the level, you can change the Lie algebra, and yeah, there are so many, infinitely many possibilities to get new identities. And actually that's what happened in 1992, when Caparelli, who was a student of Lipovsky, studied in his thesis some other Lie algebra. So yes, I will write that here. So yeah, maybe I read just a sentence to summarize what I said. So if you consider other Lie algebras or other levels, then you get new identities. And so the first historical example after that was Caparelli in 1992, this time I wrote the date, who studied the level 3 again modules, but this time of some other Lie algebra, A22, yes. So again, you don't need to know A22, but it's a bit related to A2 if you replace n by 3 in that example. So he studied that. Well, you don't, that's just for your culture, but you don't need to understand the motivation. And again, for the infinite product side, he used the Wildcats character formula. That's actually always how it's done to get the product side. And for the sum side, he did a bit the same thing as they did. He tried to construct a basis. But actually, in those things, in this approach, constructing the basis is not that easy in general. What they have easily is a spanning set, and then they try to reduce it by using some relations given by the Lie algebra. And then often it happens that representation theorists are stuck at proving that the reduced generating family is also, the reduced spanning set is also free and therefore a basis. So that was exactly Caparelli's problem. He had a conjecture for the basis, but he could only show that it's a spanning set. So it was a conjecture at that time. So maybe I will write his identity. Okay, so for all n, so the number, maybe I will just write it short, so the number of partitions of n into distinct parts congruent to 0, 2, 3, or 4 mod 6 equals the number of partitions of n that I write as usual, lambda 1, etc., up to lambda s, such that so lambda s is different from 1, you don't have a 1, and you have, as usual, some difference conditions between two consecutive parts, lambda I and lambda I plus 1, which is either 2 if both are congruent to 0 mod 3, or if they add up to a multiple of 6. and it is 4 otherwise. Okay. So, as you can see, this is already starting to be a bit more complicated than Rogers Ramanujan or Schur in terms of difference conditions. So, even this identity, I think it's unlikely that it would have been guessed without the use of representation theory. And that is actually even more true for more complicated identities that are conjectured using representation theory. Because, for example, in quite a number of them, you can have, for example, 8 by 8 matrices of difference conditions, which combinatorially seem highly non-trivial. So that's also why I like this interaction between those two fields, because really the representation theory gives us more insight on more complicated identities that we can find. And in the other direction, what I like is that as a combinatorialist, I feel very useful to representation theorists, because whenever I'm able to prove a partition identity, which was just conjectured, then by equality of cardinality, that shows that actually their conjectured spanning set is indeed a basis, because I show that the cardinalities are the same. So it's really good in both directions, I think. So that's why I love this subject. So initially it was a conjecture, as I said. So initially a conjecture, because it is not easy to prove that the conjectured basis is actually a basis. Yeah, but spanning set is easy. And it's the fact that it's free that is hard. Okay. So that was a conjecture. And actually, I also love the story that I'm going to tell right now, because I find it funny. So it was a conjecture, and Lepofsky went to a conference around that time, also in 1992, and he presented the work of his student Caparelli, and he said that, okay, there is this conjecture. And I guess I wasn't there, because obviously in 1992 I wasn't that old, even though I already liked math, but so I wasn't there. But I've been told that Andrews was in the audience and around the beginning of the conference. And Andrews was speaking a bit later in the conference, and he was supposed to talk, I don't know about what. But when he actually came to give his talk, the title of his talk had changed, and it had become a proof of Caparelli's identity. And he had actually proved that identity quite quickly using generating functions and a bit of combinatorics and two binomial coefficients and things like that. So quite efficient, right? So actually the proof is Andrews in also 1992. Then there was a weighted word version of Andrews again, but this time with Aladi and Gordon, because as we saw yesterday, they were the inventors of that method. So weighted word version. So Aladi, Andrews, and Gordon in 1993, I think. But in 1994, Caparelli came back, and he actually gave also a purely algebraic proof of his conjecture. So actually, it's also possible. From that side, it's just harder, sometimes. So algebraic proof. So that's Caparelli in 1994. And then there have been other proofs. Also, around the same time, there was another algebraic proof of Tomba and Xier, and there have been other combinatorial proofs, including one by myself relatively recently, which I will maybe just mention. Yeah. Okay, so what else can I do? Yeah, I think before continuing on Caparelli's identity, that Those other algebras or other levels, I said they give many new identities, so there have really been many new identities like that. Well, I don't know the exact number, but at least 10, maybe probably more. So, but often the identities are conjectural. Sometimes they are proved, it depends. But often they are really in a shape like that, so completely non-refined and non-weighted words to begin with. So combinatorially, it's sometimes or often interesting to actually find the weighted words version, just like Aladi and Andrews did. So, for example, because I said I would mention my research, I did find a weighted word version of an identity called Sziladich identity, which was also done by studying some, so it was, yeah, A22 still, but at level 1. And that's one of those that had like 8 by 8 difference condition matrix. So I'm not going to write the matrix, but I'm just yeah, telling you that. Yes?
Do you know if Caparelli's proof was influenced by the combinatorics at all?
Good question. I'm not sure, but I would lean towards no, but I'm not sure. Okay. Yeah, I should ask him maybe. I can tell you, yeah, if he replies to me. Yeah. But it's a good question. Okay, so yeah, so I mentioned quickly this thing about Sziladich, but I will stay a bit more focused on Caparelli, because as usual, I have to make some choices in what I say. So maybe I can write quickly that weighted words version of Caparelli. So yeah, maybe it's safer to take a new blackboard. So you have a question? Do you have a question? No? Okay. So the non-dilated version of Caparelli, I will write it here. So actually, so this is due, as I said here, to Aladi and Rosen-Gordon, but I slightly reformulated because I want to make the connection with another identity just after. So let's say it's their theorem, my formulation. So you consider integers colored in 3 colors, A, C, and D. Of course, if you see following, you're thinking, why no B, right? But the B, you will understand very soon why it's not there. Trust me. So far, just 3 colors, and no B. And the difference condition matrix is the following. Oops. Yeah, actually, in this formulation, I think it's kind of nice because you first put 2's on that kind of hook, and then you put 1's, and then you put a 0. So I don't know, I like it. I think it's a nice shape. And so the generating function for the partitions that is in those colors, colored integers satisfying those difference conditions is minus AQ, Q squared infinity, minus DQ, Q squared infinity, Q squared infinity. And if you want to find the usual Caparelli again, you should do, maybe I write it here. So you should do, you should transform the integers Ka into 3k minus 1, Kc into 3k, and Kd into 3k plus 1. So that gives the regular Caparelli. Yeah, maybe. Yeah, original is better than regular. I don't know. That Caparelli there, original Caparelli. Yeah, and those transformations, they correspond to doing Q3, A, Q minus 1, well, C, nothing special, just 1, and D, Q, if you want the correspondence. Okay, so this is a non-dilated version of Caparelli. And actually, here I will present another identity that I worked on, which is due to prims. And okay, so prims identity. Prims. Actually, it's prims, but primses, it's super hard to pronounce. You can try as an exercise. Yeah. So maybe it's better to say the identity of prims. So yeah. Okay, so this was also coming from representation theory, but from a slightly different approach. So this was obtained by studying, again, you have some level and some module. Some Lie algebra. So the Lie algebra is A11, again, just like for the Rogers-Ramanujan identity, but the level is 1 instead of 3, so again, some little change here and new identity. And actually, so it's using something called crystals, or crystal bases. So it's yet another approach. So again, if you want to find an identity using this approach, it's part of the initial idea is the same, which means that actually the product side, that will always come from the Wildcats character formula. But for the sum side, or actually here, have some labels on them, and those labels, they encode some kind of relations that exist between those elements. I hope you're okay with that. Again, if I have to define everything, that would sadly be a bit long. So, okay, so actually you consider this crystal, you just see it as a graph if you don't know anything about crystals, and that's okay. And actually I don't like to have those big labels for the vertices, so I'll just say that we will call this one A, this one B, this one C, and this one D. So you see it's the same letters, but now there is a B. So you might start to see why I didn't put it here so far. So, okay, so prims, he said, okay, so we consider again, partitions into colored integers with an order, and we are quite lucky, or at least our prims did things well, because it's just like the simplest order that you can imagine. You put all the ones first and the letters in lexicographical order. And he also defined a matrix of difference conditions. So now it will be 4 by 4, A, B, C, D. So okay, I give you this one. Okay, so this is the matrix of prims. And actually, so this matrix, so far it just looks like a matrix to you, but actually he obtained it thanks to this crystal. And this matrix is called an energy function for the crystal. There must be some physics motivation behind the name, but I'm ashamed to say that I don't know exactly where it comes from, this name, but this is an energy matrix finally, if you have some crystal, you can try to compute its energy function, and using some other character formula. So I told you there was a Wildcats character formula, there is this one, just the definition, and there is also another one called the KMN squared character formula. Why KMN squared? Because the authors are called Kang, Kashiwara, so 2 Ks, Misra, Miwa, 2 M's, Nakashima and Nakayashiki, 2 M's, so KMN squared. So yeah, so there is a KMN squared character formula that expresses the characters in terms of generating functions on some graphs on this graph, which are also depending on the energy matrix. And then Prims was doing some correspondence between those paths and some partitions. And he conjectured that the generating function for these partitions, where we replace Q by Q squared, just A by Q minus 1, B and C by 1, and D by Q. He conjectured that the generating function becomes 1 over QQ infinity. Like super simple. Just the generating function for partitions without any condition. So you can think, okay, that's kind of strange, right? Like you start with something quite complicated, at least when you look at it, and you end up with the most simple thing that you can imagine. And indeed, that's intriguing, but actually in 2017 it was, with Jeremy Lovejoy, we proved that indeed the conjecture is true. But if you actually keep the color variables A, B, C, D, actually you cannot keep B, so just A, C, D, then you obtain indeed an infinite product, but more complicated than this one. But when you do those transformations here, maybe I'm hiding them, but those transformations here, then you find indeed what Prim's conjecture. So maybe I can just write quickly. So theorem. So that's me and Lovejoy. That's 2017. Actually, the generating function is with b equals 1, because otherwise, if we don't take b equals 1, we don't have a product. So the generating function is minus aq q squared infinity minus dq q squared infinity divided by qq infinity cq q squared infinity. And yeah, I'm not writing it, but when we do these transformations, we get that. And the conjecture is true. So, okay, so now you have the actual infinite product of the non-dilated version here, and you had the infinite product of Caparelli. So, do you see any similarity? Maybe am I hiding both of them? Maybe I'll go here, so that you can quickly look at them. So at least the numerator seems similar, right? Exactly the same even, and on the denominator, okay, there you have a factor QQ that is there but not here, and here you also have a C, but if you remove the C, you have this one, right? And so that intrigued me for a while, and actually I found, I think, apparently a year later, I have written all the data in my little notebook, that actually there is a bijection between the partitions from both those identities, and, well, a bijection between the Primsch partition and pairs of partitions, where the first one is a Caparelli partition and the second one is just some unrestricted partition, because of course we need this 1 over QQ infinity to appear. So maybe I can just write here. So in 2000, do you see what I write here, or it's too hidden? It's not going to be big in any case. So in 2018, so bijection between so primes and yeah, let's say Caparelli times partitions. Okay. So actually, those identities, they were like, they are both from representation theory, but they are not. They don't come from the same algebra or the same level or even the same method, because this one is really for coming from this crystal approach, and this one is from this approach there, which is called the vertex operator algebra approach. So it was in a sense a surprise that these two were connected. Even Prims wrote in his paper that he doesn't think it's related to Caparelli or this approach in any way, but actually, at least combinatorially, there is a connection. Okay, so I look at my watch for one last time to see how much I still have. Not so much, but I will tell you quickly what I did after that. So maybe what do I need? I put it up a little bit at least. And so I will finish with that. Blackboard. So, in Prim's paper, there was this identity, but there was also another identity which was quite scary because it was a 9 by 9 matrix of difference conditions. So, in Prim's, there was a 9 by 9 identity, and also there is some other paper of Prim's with a colleague of his called Norman, and they have also 8 by 8 matrix. So the 9 by 9 was coming from the crystals, not of A11, but of A21. So A21, and this one I don't remember where it came from, but some other representation. Okay, and I had enjoyed a lot, like this work on Prim's identity, the 4x4, so I wanted ideally to be able to also prove combinatorially and refine the 9 by 9. And actually, so the 4x4 was a conjecture, but the 9 by 9 he had proved already. And actually, I think he could also have proved 4x4, but somehow, I don't know. Yeah, that happens. So yeah, so what I really wanted was just to refine it. And I started to work with the student at the time of Jeremy Lovejoy, whose name is Isaac Benon. So with Isaac, actually, we were stuck for a while, but instead of just proving 9 by 9, in the end it was almost easier for us to fully generalize this to n squared by n squared. Sometimes it happens, like, if you generalize more, you see more structure, so that was what happened. So actually, so I think that was 2019. So generalization of Prim's 4x4 and 9 by 9 identities. So actually we found some difference conditions that are not even that hard to write. So maybe I'll write it here, maybe you'll see that actually it can be, once you see it the right way, it's not that difficult anymore. So you would just have colors. The colors will be AI, BJ for IJ, IJ between 0 0 and n-1. That way we would get n-squared colors, okay? And actually the difference conditions, so the minimal difference between the part colored AIBJ and the part colored AI'J prime, BJ prime, sorry, is, so chi of I larger than I prime minus chi of I equals j equals I prime plus chi of j at most j prime minus chi of j equals I prime equals j prime, and chi is just the function. You know, it's equal to 1 when the thing inside is true and 0 otherwise. Okay, so I mean, it's not like really, really simple, but if you had seen the 9x9 matrix, you would be happy to have that instead. And it's also nice that it works for all n, actually. And so we showed also that we have a non-dilated version, but let's not, because I'm at the end of my time, I will just say that the dilated version of the generating function is 1 over QQ infinity, like in print, but actually we have a slightly, not that complicated, but just a bit more complicated formula with colors. So we have actually the version. And through generalization of my bijection here, we also proved a generalization of Caparelli's identity, which also contains this 8x8 identity of norm and Primch, and more generally an infinite family. And I will end by telling you, without writing anything, that then once we found these difference conditions that generalize those two matrices, the natural question was to ask whether it was also the energy function for some crystal, because initially we really just generalized it from the combinatorial point of view. And actually, indeed, we were either lucky or math is well done. But this is actually indeed the generating function for the level 1 crystal of n-1, And thanks to this, we also tried to work a bit more on the representation theoretic side. And actually, we found in some subsequent paper bijection between that Kmn squared character formula that I mentioned, which expresses the characters as paths on this crystal graph, with partitions which have some restrictions and which we call the grounded partitions. Like you have to fix the smallest part, and then the difference conditions are given by the energy function. And by generalizing this more and more, we were actually able also to find results in representation theory. For example, we found new character formulas for certain the algebras that hadn't been, or at certain levels that hadn't been studied before. And the advantage of the character formulas we get are that the coefficients are obviously positive, and that's something that you like in general in characters. I think I just erased the wrong blackboard, but if you remember, the character was defined as a generating function for dimensions, if you want. So obviously dimensions, they are positive. But if you look, for example, at the Wildcats character formula, it's not obvious that the coefficients are positive from looking at the formula. So one type of research that can be done about characters in representation theory is trying to find obviously positive formulas. And our combinatorial approach allows us to do that. So yes, that's more or less where we are at now, and this is still ongoing. Like we're still studying some other algebras or trying to generalize further. So yeah, this is really what I'm doing at this moment. So thank you very much.